All right, so I'm going over solving systems by graphing, and we are going to be using technology for this. We'll do a few by hand, and then we'll verify it with Desmos because, you know, it's a lot faster to use technology than to graph these things by hand. And welcome, Jason. I just got started, so glad that I kind of waited a couple minutes. So. Okay, so first I just want to start with vocabulary. What is a system? So a system is what we refer to as two or more equations that we are solving a single answer for all the equations, so it has to work in all of them. And so when you have two equations, you have an ordered pair with an answer with an x and a y. And we indicate we have a system with a curly brace kind of surrounding the equations to tell us these are considered together. Now, in engineering, these are often referred to as simultaneous systems or simultaneous equations instead of linear systems or systems of equations, because you're looking for an answer that works in all of them simultaneously or at the same time. And since our solution is an ordered pair, this tells us that we can graph these things, especially because you have an x and a y, and those are always associated with graphing. So we can always solve systems graphically as long as you have two variables. If you have three variable systems, you can graph those, but they're a lot more difficult to visualize. And if you have a more complicated system that's four or more, you can't graph it because we can only graph things in 2D or 3D. So when you graph these, your solution is where your graphs are intersecting. And so graphing is nice as a check that you can check to see if there's a solution and how many solutions there are. So I've got an example of one solution, two lines, they intersect at one point. You can have two solutions if you have a line and then you have like a quadratic, so that line can go through it multiple times. And you can have no solution if they don't intersect at all, and that is entirely possible. So there are some pros and cons to graphing and solving by graphing. So the pros is that it's really easy to see, are there solutions, where are they located? You can see how many solutions there are. With technology, it's really fast, and I would actually recommend when you guys have the proctored exam in week 5 that you do these by the graphical method to save yourself time, because the proctored exam is timed. So that's what I would do for the proctored exam. It's a good way to check your work if you're solving with a different method. So if you solve with substitution or elimination, you can then graph your equations and see if that intersection matches what you got when you solved. And if you have things that are not lines, so if nonlinear, you have quadratics or absolute values or other things, those are usually more difficult to solve, like using substitution or elimination, and so graphing is easier for those systems. So basically my go-to is that if I have two lines, I'll solve with substitution or elimination, otherwise I'll use graphing. Now there are some cons to doing this by graphing, which is if you don't have technology, when you're graphing by hand, you could get incorrect answers because your graph is not correct, or it's not to scale. Like if you don't use graph paper, you can have things slightly off. It's just very difficult to get exact answers graphing by hand. The other con is that if it's a decimal answer, or it's something that sometimes you can have answers that are like square roots. When you graph it, you don't know the exact answer, you just get a decimal approximation. And so that's downside, because then if you go in and check your work, it may not match exactly because it's not an exact answer. And then another con is that depending on where your graph, usually when you graph in Desmos, it kind of centers at the origin. But if your ordered pair of where they intersect is way far out, you don't really know where to look for it. So you have to kind of scroll and click and drag and zoom in and out to try to find the graph. And so that is a downside, because you're just messing with the technology to try to figure out where it is. So there are pros and cons, but I usually use the graphical method just for checking work, but I would recommend using it for the proctored exam. So when you have linear systems, so you've got two lines or three lines if it's 3D, but basically let's assume we've got two equations and they're linear, so they're lines. You get one solution when they intersect. So they intersect at a single point. And you can tell, and let's say your equations are in slope-intercept form, y equals mx plus b. If you have your two equations and they have different slopes, you automatically know there's one solution and they're going to intersect. Because if you have two different slopes, they're going to cross somewhere. Now with two lines, you could get infinite many solutions if they are the exact same line. So they have the same slope and the same y-intercept. This usually happens if they're not in slope-intercept form and one equation is maybe a multiple of the other. So if you have equations with like x and y on the same side, that's usually where you might see that you have infinite many solutions. They're the same line, they just don't look like they're the same line. If you solve your equations for y, you can always determine if they're the same line or not. And when we write solutions for infinite solutions, we have a form where we write it as an ordered pair, where you have a variable a, and then you plug a into your equation. So it would look something like a and then ma plus b, which whatever the number is for the slope or the y-intercept. That's how we kind of write those solutions. And then there is a possibility that your lines never intersect because they're parallel, so you have no solution. And parallel lines have the same slope. So if you see, if they're both in slope-intercept form, and you see they have the same slope, but their y-intercepts are different, that means there's no solution. And solutions or systems that have no solution we call inconsistent. If there is a solution, even if it's infinite many solutions, those are considered consistent systems. So that's how it works with linear. So now I just kind of wanted to go over all the vocabulary and everything. Do you guys have any questions before we go to the examples?
Can you just wait a few seconds on this screen? I'm almost done copying.
Sure thing.
Thank you.
And you can always download the PowerPoint when I send out the email with the video. I always include the PowerPoint as well. So if you miss something, you can always check that out on the PowerPoint.
Okay, cool. Thank you.
So just let me know when you're ready.
I'm ready.
Okay. So I've got, let's see, I've got about 7 examples that we're going to go through. Some are lines, some are not. And so we're going to kind of solve these by hand, and then I'm going to also use Desmos so that you can see the comparisons here. So we have the system x plus y equals 0, and then 2x minus 7y equals negative 18. So when my x and y are in the same side, I choose to graph using my intercepts. So I'm going to just color code, so that way I can color code on my graph. And then I can also color code my work. So the equation x plus y equals 0, I'm just going to make a table. And I'm going to find my intercepts. So I'm going to find the y-intercept, which is when x is equal to 0. So when x is 0 and I plug 0 into my equation, I just get y equals 0. And then when I plug y into the equation, I get x equals 0. Which just gives us the same ordered pair. So in this case, that wasn't helpful. I just have only one point here. So I might want to pick another point. So make that look like a 0. So let's say I'm going to pick an x value of 5. And I just picked that because it's my graph goes till 10 basically. So I just picked halfway. So if I plug 5 in for x, I have to subtract the 5 from both sides, because I get 5 plus a y equals 0. So we get y equals negative 5. So I'm going to graph that. And then I'm going to attempt to connect them with a line. I've got a ruler here that I'm going to try to use on my computer screen. We'll see how well this goes. can get it. Okay, not too bad. And now let's take a look at the second equation. We have 2x minus 7y equals negative 18. So I'm going to use the same method where I'm finding the intercepts. So when x is 0, I'm solving negative 7y equals negative 18. So I have to divide both sides by 7, and it's going to give me a decimal. The exact value would be, we usually write it as a fraction, but for graphing purposes, decimals are easier. And so I'm just going to kind of round it, and I have to kind of eyeball here. So negative 18 divided by negative 7 gives me 2.571, and it just keeps going. So I'm going to round it to about 2.6. And so I have to kind of guesstimate at where that's at. Maybe make it a little bigger. It's somewhere there. And then I'm going to plug 0 in for y, which gives me the equation 2x equals negative 18. So when I divide both sides by 2, I get negative 9. So 1, 2, 3, 4, 5, 6, 7, 8. I got to make sure I'm reading my lines correctly. So now I'm going to draw my line through there as best I can, and then I'm looking for the intersection point and estimating where that is. So you can see where it crosses, it's not actually on our grid, which is going to make it a little more difficult to estimate where that is. So if it looks like it's between -1 and -2, so maybe like -1.9 on the x. And on the y, it's a little bit bigger than 2, so maybe 2.1. I'm kind of guessing here based off of what I'm looking at with my grid. So I'm going to estimate my solution based off of my grid as best as I can as I'm going to label this as by hand. This is my by hand answer. -1.9 and 2.1. So let's actually use Desmos to get the exact answer, or at least as best we can, and see how good we are by graphing by hand. So I've got Desmos open here. And I'm just going to hit graphing calculator. And then I'm going to enter in the two equations. So I just type exactly what I see. X plus y equals 0. Oh. And then I hit enter, and then I type in my other equation, 2x minus 7y equals negative 18. Okay. And then it actually highlights our intersection point, and it's actually a whole number, -2 and 2. So my graph was off, and because mine didn't go through exactly -2, 2, but that's the exact answer here. So using technology or using Desmos, we can get the exact answer, -2, 2. And this shows you one of the cons of graphing by hand, because when you graph by hand, if your lines are not exact, you're not going to get the right answer. You get close to it, but it may not be the right numbers. So if you rounded mine to whole numbers, I get -2, 2, but my graph doesn't go through that point because that would be right here. Oops. Yeah, if it would actually draw, there we go. So that's where the actual intersection point is, that little dot in green, and mine's close to there but doesn't actually go through it. So this is why I recommend using technology for graphing, because you may not be exact. Are there any questions? Okay, and this is a good situation where solving by, using substitution or elimination would be more accurate, because you'll get the exact answers that way versus graphing. So here's an example where we have something that's not a line. And when it's not a line, that's definitely where I want to graph by, use technology, because graphing a natural log, I mean, you can do ordered pairs and all that kind of stuff, but it's a lot harder to graph. But I'm actually going to do this one by hand first, just to reinforce how to graph a natural log. And then we'll use technology again. We'll use Desmos to kind of compare how accurate our answer is by doing it by hand versus actually using technology. So I'm going to do the color coding thing again. So our first equation is y plus 2 equals the natural log of x minus 1. So when I'm graphing a natural log equation, I prefer to have it solve for y, and then I use function transformations. So if I subtract 2 from both sides, I'm actually going to graph y equals the natural log of x minus 1, then minus 2. And so the natural log of x, when we graph this with an xy table, we've got 3 key points on y. We've got -1, 0, and 1. And I got to make sure that I'm remembering these correctly, because the natural log is the inverse of e to the x. So e to the 1 is e. So this would be the value of e, which is about 2.172, I think, is about what that point is. And then 1 over e would be right here. And so that's approximately, if I do that on the calculator, finding the button on my calculator, 0.4-ish. So those would be the values for the natural log of x. And then we're having a transformation. The x minus 1 means we're adding 1 to x. So all of the x values get added by 1 because of the x minus 1. And then the minus 2 means we're subtracting 2 from y. So if I was to graph this by hand and using transformations, I'm going to add 1 to all my x values. So this is going to be about 1.4, 2, and then 3.72. And then subtracting 2 from my y values. So that's -3, -2, and -1. And I'm going to just verify one of these points. I'm going to plug in 2 for x and just make sure that when I plug that into the natural log of x minus 1 minus 2, that I get the correct number here. And yes, that gives me -2. So again, I have to kind of estimate where these values are when I'm graphing, which is going to make it very difficult. And 3 about there. And then a natural log shape looks something like this-ish. So that's my approximate graph of the natural log. So now I'm going to graph by hand the 3y plus 2x equals 9. So again, I'll color code here. And I'll use my intercepts. So when x is 0, I'm solving 3y equals 9. So that gives me y equals 3. And then when y is 0, I'm solving 2x equals 9, which gives me 4.5 for x. So I'm just going to plot my points. And then this is a line, so I'm going to connect these two dots that I have, and as best I can, And there we go. So by hand, it looks like our ordered pair is maybe at 6, 0, because that's where I have my things crossing, and I actually have it going through one of my numbers. So let's now put this in Desmos and see how correct I am by doing this by hand. And hopefully, if I'm lucky, I'm actually pretty good and I'm pretty correct, but we'll see. So I'm going to just delete these two. And you can enter it in as it was originally. So our first one was y plus 2 equals. And then if you just type ln, it will automatically do the natural log. Now we have x minus 1. And then we've got our second equation, 3y plus 2x equals 9. Okay. So according to our graph, our correct answer is 5.309 and negative 0.539. So I had the solution here at 6, 0, and it's actually here, which again, my graph is not exactly correct by graphing by hand. It doesn't give me the exact answer. I'm actually further away than I was on the previous with the lines. I actually did worse graphing this one by hand. And that's because it's harder to graph something like a natural log by hand. So this is an example where if you have something that's not lines, you have like a natural log or any other stuff, graphing by using technology is a lot easier, it's faster, you just type in the equations, and it's more accurate. Now this is an approximation because there's decimals. We don't have, there may be more decimal places than we're seeing here, but it's a better answer than what I got by graphing by hand. So Desmos tells us the exact answer is negative 5 point, what was it again? Oops, 309. Now that was a positive 5.309, and then a negative 0.539. And so that is the actual answer, which is lower than where I actually had my answer, somewhere around there. So when you see something with a natural log or something that's not a line, I would not, I mean, you can graph it by hand, but I would not recommend it because your answer, my answer, was further off, and it's harder to get a good solution that way because it all depends on how accurate your drawing is. And my drawing was not exactly accurate. So, you know, none of my line doesn't go through that point, neither does my natural log graph. They're close, but they don't hit that. So here's another one, Emma. This is something that we've got our first equation, which is a line, and then our second equation, which is actually an equation of a circle. So I know this is an equation of a circle because it has an x squared and a y squared. So in order to, if you were trying to graph this by hand, you would have to complete the square so that you could get it in the form x minus some number for that quadratic on the left. And then you'd have your plus y squared equals a number. So you'd have to complete the square on the left to put it in the correct form for a circle. And that's going to be a lot of work. Completing the square is not an easy process. And so to graph something like this, you know, to graph it easily, to get the circle correct, there's a lot of work involved. So this would be one where I wouldn't even try to graph this by hand. I would go straight to using technology. because it's not, we don't have this equation that's in an easy way to graph. So I'm just going to go to technology, go to Desmos, and then I'm going to, after this, copy that graph onto this screen so that it's in the notes. But we're going to just go to Desmos immediately for this system, because otherwise it's going to be harder to graph it. So I'm going to just see if I can kind of dual here. So I've got negative x plus y equals 3. And then x squared minus 6x minus 27 plus y squared equals 0. And there's our circle. So we have two solutions here because we've got 2 points at where they intersect. So we've got 3, 6. And then we've got negative 3, 0. So we have 2 solutions, and that's easy to see with the graph. It takes virtually, less than a minute to type this in and to get your solutions. Versus if we tried to put it in the form so we can graph the circle, that probably would take at least 5 minutes just to go through the completing the square process and then having to graph it. So Desmos, wonderful. Just plug in your equations here, and then you see we've got 2 solutions and what they are. So we've got Desmos. We have 2 solutions. We had 3, 6, and negative 3, 0. Well, let me just double check that. And I don't have to click on this dot. I just have to hover over it with the mouse. 3, 6, and negative 3, 0. So there's our solutions. And if you wanted to try to solve this one by hand, like you'd have to use substitution. You'd have to maybe solve the first equation for, if you solve this first equation for y, you could plug that into the second equation. Then you have to square it, which means you have to FOIL something out. Then you have to add all of your like terms. Then you're going to end up with a quadratic that you need to factor. So then you have to factor your quadratic to get your 2 solutions. And then that will give you your x values. And then you have to plug them back in to find the y values. So that's a lengthy process. That probably takes just as long as doing the completing of the square. And so if it's not easy to solve by hand using algebra, I would graph it. So this is another one that I would graph because we've got y equals e to the x. And we have to kind of figure out if we're, solving this by hand, if we were trying to do a substitution problem, would be very, very difficult, because if you try to plug in e to the x in for y in your second equation, how do you solve for x? We have an x in and out of the e. It's very difficult to solve this using algebra. So I would solve this by graphing. Now I'm going to just graph this by hand, and then once again I'll compare it to the actual one in Desmos, because this isn't going to be too bad to graph by hand. I just have to plug in numbers into my table for the e to the x. So if I plug in -1, that gives me that 0.4-ish that I had gotten before. E to the 0 is 1, and then e to the first power is that 2.7-ish number. So I'm going to attempt to graph these really badly. Something like this. So that's my e to the x roughly. And then this x minus y plus 1 equals 0, I could just put this in slope-intercept form by adding y to both sides. And we get x plus 1 equals y. So the slope is 1 and the y-intercept is 1. So that's my y-intercept. And then the slope means it goes up 1 over 1. So I can use that slope to get enough points that I can plot my line here. And then do my best to actually go through that. My line doesn't even touch my initial dot. But I did get an overlap here. 0, 1 was on my the blue graph, the e to the x, and it's on my orange graph because that's the y-intercept. So I know by hand, even though my picture is terrible, I know that by hand the solution is 0, 1. And that just happens because I happen to get that same number on both when I was graphing. And I'm sure you can hear my unhappy dog barking in the background. So let's just graph these. So I'm going to do y equals, and you could just type the letter e and then get in the exponent. So that's e to the x. And then x minus y plus 1 equals 0. And you can see that, yes, our answer is 0, 1. So this wasn't too bad to do by hand for graphing, but I did get the same answer, but you can see that like my graph isn't all that great. But I certainly would not want to solve this using substitution because it would just be really, really difficult. Are there any questions so far? Okay.
So I'm trying to just graph this in the calculator, the Desmos calculator, like you are.
Mm-hmm.
So when I put y equals ex, I'm coming up with a 90-degree. I don't have the slope.
You don't have the curve?
No, I don't understand.
Are you in the exponent?
Yeah.
Okay.
Huh. I'll try it one more time.
Yeah, like I've been hitting the number or the symbol above 6. The caret puts me in the exponent. You can also use this little button here to get in the exponent. It could also be depending on how zoomed in or out you're in, because if you zoom out enough, it looks like a 90-degree angle.
That's what it is. Okay, sounds good.
Okay.
That's a
good question. Yeah.
Right.
So that is actually, when you're looking for these intersections, you do want to make sure you're zoomed in enough. But if you zoom in too much, you can kind of see that it looks like it overlaps in lots of places. So there's like a sweet spot you need to be in. And that's one of the cons actually that I had on that list is, you know, you have the window. If you don't have the window right, it can look wrong. So.
Okay. Sounds good. My bad. Like I said, I see what you're talking about now. I was too far out and it looked like an angle. All right, cool. That answers that.
Okay. So there's no other questions on that. I do have a few examples, word problem examples with real data, just to kind of, so you can see how these connect to real life and how you, when you have real life data, graphing it actually might be preferred. So this actually comes from section 7.1. It's number 62. And so we have a table of the consumption in trillions of BTUs of geothermal energy and wind energy in the United States, 2004 through 2014. So part A says to use a graphing utility to find a cubic model for the geothermal energy consumption data and a cubic model for the wind energy consumption data. So this is something that is basically you're trying to find a cubic polynomial that fits that data. You can do this in Excel. Excel actually has an option for a trend line, and you can choose polynomial trend lines, and then you can tell it you want something that's cubic or degree 3. So part A, they want you to basically come up with those equations and then to graph them. And then part C is to use the graph to approximate the point of intersection, interpret the answer in the context of the problem, and then we've got to describe the behavior of each model. Do you think the models can accurately predict the consumption of geothermal energy and wind energy in the United States for future years? So I did parts A and B already in Excel. You guys don't need to know how to do this. If you want on your own term, you can kind of play around with it, but I actually went through and graphed them and then made the graph so you can see what the equations are to kind of best fit you know, the data that we have. And so the part that I wanted to focus on was to use the graph from I apparently missed the word part A or part B when I was typing this. Here's the graph from part B to approximate the point of intersection of the graphs of the models. So you can see the intersection point right about here. So the way that our horizontal axis is these are counting, basically these are the years, so like 4 is out 2004. So this point right here is 2005. So our intersection is a little bit after 2005, but it's not 2006. So it's like sometime in the year 2005. It's not in January because the first point we'd be assuming it would be January. So maybe by February or March of 2005 is where the intersection point occurs. So then we need to kind of estimate what is that Y value. So it doesn't quite hit my line at 200. It looks like it's a little bit under, so maybe 190 or something like that. So we would be estimating this like maybe it's at 5.1 and 190. You're just kind of making an estimate because, you know, we're just eyeballing it based off of the graph. If you typed those equations into Desmos, you could get the exact intersection point of the two graphs if you wanted to attempt to do that, but we're approximating here. So what this means, if we're interpreting our answer in the context of the problem, we could say, okay, if it's about 5.1, there's 12 months in a year. So that's maybe 0.1 is like in February or something like that. So we could say around February of 2005, because it's a little bit after the start of 2005. Both, because it's an intersection, so this applies to both the geothermal and wind. Both geothermal and wind. And now I'm going to go back to what it tells us about the table. This is the consumption of the BTUs. So consumed, and the units were in trillions, about 190 trillion BTUs. So that's essentially what the intersection means. It's where both the geothermal and the wind consumption were the same. And so according to our data here, that would be around February 2005, and that would be 190 trillion BTUs based off of our estimate. Now part D is said describe the behavior of each model, which is basically, okay, you're looking at it, they increase. One is increasing faster than the other. Do you think the models can accurately predict the consumption of geothermal energy and wind energy in the United States? That's an opinion. That's, you know, there's no right or wrong answer to that. Looking at the current data, it looks like they fit pretty well, like all the dots are pretty close to our graph, so I would say yes, but there's not really a right or wrong answer here because there's so many factors that could be happening. So this is one example from the textbook of using real data basically here to kind of estimate where that pinpoint, that overlap would be. Are there any questions on this example? Okay. Now this is also from 7.1. This is number 70. So they've already given us the graph here. And so this is a cost versus revenue graph. And this is used a lot in economics. And this is really useful for anybody that's related to business because it's usually easier to see these things graphically. So we've got the cost of producing X units and the revenue obtained by selling X units. So we've got cost and revenue. So estimate the point of intersection, and then what does this point represent? So the intersection point, if we're trying to read it here, it looks like, so it's halfway between 2,000 and 3,000. So maybe 2,500. And then it does look like it's exactly on the line, 150,000. So that would be our estimated point of intersection. And this point represents where your cost is equal to the revenue. That's what this means. This is usually called the break-even point. Even. So it's where your cost is whatever you're spending. The revenue is the money you're bringing in. It doesn't actually represent the profit, but it just means you're bringing in the same amount that you're spending, essentially. So that's the break-even point. And then it's just to use the figure to identify the X values that correspond to an overall loss and an overall profit. So you get a loss when your costs exceed your revenue. So our loss area is right there. And then you make a profit on the other end when your revenue is above cost. So looking at it graphically is really nice because you can see where am I making money, where am I going, where am I losing money. So part B says to identify the X values. So we're basically writing this in interval notation. The loss is between 0 and that intersection point, 2,500 for the X. And actually, I should have an open parenthesis at 2,500 because at 2,500, it's not a loss, they break even. So I can't actually include the break-even point. So it's below the break-even point, basically, where we're losing money. And then it's above the break-even point. And we don't have an endpoint, so basically to infinity, where we are gaining money. So 2,500 to infinity, because according to this graph, I mean, I don't know where it ends. But anything larger than 2,500 units, we would be making a profit. And the explain is basically everything I just said in words. And then I've got one more word problem here. And again, I graphed this one in Excel for us so that way you can compare them. So this is pharmacology. The number of prescriptions, P in thousands, filled at 2 pharmacies from 2012 through 2016 are shown in this table. So this is coming from 7.2. This is problem 53. So part A asked for you to basically graph it and then come up with a linear model. So we're just using a line and then getting an equation for a line that goes through those points. So I've got those equations on the right, so if you want to verify them, you can. Part B, assume that the models can be used to represent future years. So that basically means assume that you would extend these lines out, which I have terrible lines here. If I try to use my ruler as best as I can. Okay, that looks a little better. Okay, those look much better. So assume that you can extend the lines out, basically. will the number of prescriptions filled at pharmacy A ever exceed the number of prescriptions filled at pharmacy B? And then if so, when? So PowerPoint wouldn't let me really change the colors on this. So I'm just label this bottom one is A, the top one is B. They're very similar blues. That was the best it gave me. So you can see by the equations they don't have the same slope. So I had said at the very beginning that if you have two lines and their slopes are different, they're guaranteed to intersect. So if they're guaranteed to intersect, then at one point they're going to intersect and then A will start exceeding B, because they have to, in order to have intersect A, it has to get closer to B. And you can see as I extended those lines that they are getting closer and closer together. So yes, the number of prescriptions filled at pharmacy A will exceed the number of prescriptions filled at pharmacy B. Now the question is, if so, when? Well, my equation here, my graph, I don't know when that is because I can't see it. It's not on my graph. So we're going to have to go to Desmos and actually type these two equations that I got from Excel into Desmos so we can see when that will be. So move this over so I can actually see my equation. So I'm going to type equation A in first. It was 0.52x plus 12.86. And then pharmacy B is y equals 0.39x plus 15.7. Okay. So this is one where immediately the way that it defaults in Desmos, I can't actually see where they intersect. So you can zoom out and then kind of move things over. And then you can see that they do intersect somewhere here. So I'm going to click one of the lines, and then that gives me the intersection point. So they intersect at 21.846 and 24.22. Now, our horizontal, our x values, these are the years. And 12 started with 2012. So, and then we would graph 2013 as 13. So getting a number of 21.846, if you rounded that to a whole number, it's about in 2022. You could say between 2021 and 2022 is when they're going to be equal. So then you can say, okay, if they're going to be equal sometime between 2021 and 2022, then it's safe to say that pharmacy A will exceed pharmacy B in the number of prescriptions in 2022, because if we round it up, if we go to 2022, which would be somewhere, I can click and drag, and I can even kind of zoom in here. But 2022 is this big, more solid line here. It's hard to see, but the purple line is, if you zoom in enough, higher. So this pharmacy A is higher than pharmacy B, which is the black line here. So going back to this word problem in part B, yes, it will exceed, and then it would be in about 2022, roughly, we can say, is when pharmacy A will exceed those of pharmacy B. So we're using a lot of technology here. Excel is really nice if you're doing linear trend lines. The Excel help is pretty useful for that. Desmos can do these things, but it's harder. I feel like Excel is a lot easier to come up with the line through a series of points. It's easier in Excel than in Desmos. Desmos, you have to do a lot of coding, and I usually have to look up how to do that. But this is my last example of solving by graphing, and so you can kind of see how this is useful in real life versus looking at equations maybe. I feel like when you have real data, graphing it makes much more sense than to write an equation and then kind of looking at it, because you're just looking for the overall trend and what happens. You don't need an exact number. So are there any questions? Okay.